Hello, my good people, and welcome back to another exciting session brought to you by Odavig Structural Hub. This is a place where you learn, build, and innovate. So, in today's session or lesson, I want to tackle example number one, and this example is from stability of a dam. So, if you are a Module 2 student or a CDAC student, this session is for you. And for those who have not subscribed to this channel, please do so and hit that notification bell so that you may be the first person to be notified when I upload a video. And if you find these videos educative and relevant, please don't hesitate to share to your friends. Your friend can be your fellow classmate or your fellow comrades or your fellow trainer or any other person who is interested in this field of civil engineering. So stay tuned as I start this lesson up to the end. So the question is on the board, as you can see, and it reads, a trapezoidal masonry dam having 4 meters top width, 8 meters bottom width, and 12 meters high is retaining water up to a height of 10 meters. The density of the masonry is 2,000 kilogram per meter cubic, and the coefficient of friction between the dam and the soil is 0.55. The allowable compressive stress is 3350 Newton per meter square. Check the stability of the dam. So our question is to check the stability of the dam. So we want to check the sliding, the tension, compressive, and overturning. So let's begin solving this question. So the first thing to do is to draw the dam. So solution. So before we begin calculating the stability of this dam, let's draw it. So the top width is 4 meters and the bottom width is 8 meters. So I will draw it here. So we have been told the dam is retaining water up to a height of 10 meters. So it will be somewhere, if we approximate, around there. So this is the dam and this is the retained water. So the dam has a height. Let me draw it here. A height of 12 meters, and it has a top width of 4 meters. And this retained water, it has a height of 10 meters. So this is 10 meters. and a bottom width of 8 meters, like that. So we know that this retained water, it exerts a pressure at this one side of the dam. So we will draw the pressure, the force exerted by the body of water. So this is F. Again, that is F. And then we have a weight of the dam, which is W, at the center of the dam. So that is W. Again, this weight is acting at the center of the dam, like that. And then this force F and force W produces a resultant force, which is R, like that. So this is R. So where the R cuts the base of the dam, we call it M. And here is N. And here is A. And here is B. Like that. So we have this distance between N and M. So that distance is, we call it X. Again, we have another distance between A and M. So that is the distance. We call it D, like that. So having done so, now we can start calculating the stability of this dam. And remember, this F is acting at a distance of H over 3 from the base. So this is H over 3. And this is H. And this is capital H. This one. This 12 meters. So let's start calculating the stability of the dam. So the first thing to do is to calculate the forces exerted on this dam. So we have force F and force W. So force F, so F is equal to weight, unit weight of water, times area, times H bar, times H bar, like that. So the final formula will be W times H square over 2. Remember to consider 1 meter length of the dam. So consider 1 meter length of the dam. Like that. So our F is equal to W is the unit weight of water, and for this case we have not been given. And from the basic, we know that the density of water is 1,000 kilogram per meter cubic. So we have 1,000 kilogram per meter cubic. But since we want to calculate, we want to get this F in Newton, we will multiply by gravitation acceleration, which is 9.81. By doing so, we have now converted this kilogram per meter cubic to Newton per meter cubic, which will be the unit weight of water, times H. H is this 10 meters times 10 square over 2, which is equal to, so you will punch your calculator to get the answer. So the answer is 490, 500. 490, 500 Newton. So that is our F. So this is the force as a result of retained water exerting on this one side of the dam. Then we proceed to W. We will proceed to W. So I will erase here to create more space for calculation. So the weight W of the dam is equal to area times, no, is equal to unit weight of the dam, which is W0 times area times length of the dam. And the unit weight of this dam, as you have seen in the question, we have been told the density of the dam is 2000 kilogram. So we will multiply by gravitation acceleration, which is 9.81, to convert from kilogram per meter cubic to Newton per meter cubic, then times area. Area of the dam is a half into sum of two parallel sides, that is 4 plus 8. 4 plus 8, then times H. H is 12 meters times 12 times length of the dam is 1 times 1. Then you punch your calculator to obtain the answer. So the answer is 1412.640 Newton. And remember, this F is acting at 10. Yes, at 10 over 3 from the base. At 10 over 3 from the base. From the base. Which is H over 3. So H is 10. At 10 over 3 from the base. We proceed. After calculating our F and W, the next thing to calculate is the length, AN. This length from here to here. So AN is equal to, we have an expression to obtain AN, which is A square plus AB plus B square over 3 into bracket A plus B, like that. So our A is the top width and our B is the bottom width. So AN is equal to A is 4 square is equal to 4 square plus AB, which is 4 times 8, 4 times 8, then plus 8 square, which is this 8B over 3 into bracket 4 plus 8, like that. Then you punch your calculator, therefore, which imply AN is equal to, punch your calculator to obtain the answer. So the answer is 3.11 meters. You can also obtain AN by taking moment about A. So you will say that no, you can obtain AN also by subdividing this trapezium into two. So that one will be a triangle and a rectangle like this. So if you subdivide like that, you will get the area of this rectangle times its centroid plus the area of this triangle times its centroid. Then you will equate to the area of the whole of this trapezium times distance AN. So let's do it practically. The area of this rectangle is 4 times 12. So we will have 4 times 12. The centroid, as you are coming from this side, it will be 4 over 2 bracket plus the area of this triangle. It is a half base times height, a half. The base is 8 from here to here minus 4. So the base is 4 times height. Height is 12 times centroid. Since you are coming from this side, you will take 4 times 4 plus from here to here is 4. Then you'll have h over 3 or b over 3, which is 4 over 3 is equal to the area of the whole of this trapezium is a half times, or a half into bracket, the sum of two parallel sides, that is 4 plus 8, 4 plus 8 times h is 12. Then you multiply everything by AN. So which imply AN is equal to 3.11 meters. You can either choose this one or choose this one. So the one that will save your time, it matters a lot. So let's proceed. So after calculating distance AN, so another distance you are supposed to calculate is this distance x, which is NM. So let's see how we can calculate this distance NM. So NM, allow me to erase here. So NM, which is distance x, is equal to F over W times H. over 3. So our F was 490, 500, and our W is 14, 12, 64, 0 times H over 3, this one, 10 over 3 times 10 over 3. Then you punch your calculator to obtain the answer. So the answer is 1.157, 1.157 meters. So this is distance x from here to here. After calculating distance x and an, we now proceed to d, distance d. I want now to obtain this distance d. As you can see, d is from here to here. So we will take an plus nm, like that. So allow me to erase here for more calculation. So distance d is equal to an plus nm, which is distance x. So this one will be an is 3.11 plus 1.157. They are all in meters, and the answer is 4.267 meters. So this is distance an. Sorry, this is distance am and not an. So it is distance am, which is d. Like that. So am, which is distance d. After that, we can now proceed to checking the stability of the dam. Let's now check the stability of the dam. Stability of the dam. So we will begin by checking the tension. So number one is tension. Number one is tension. So for tension, we know that D should be less or equal to 2 over 3B. So if D is less or equal to 2 over 3B, then there will be no tension in the dam. So we know that our D is 4.267 should be less or equal to 2 over 3 times B. B is 8, like that. So 4.267 should be less or equal to, if you multiply this, you will get 5 0.33. So as you can see, it is less. So it means it is okay in tension. So therefore, okay in tension. So we are done with tension. We proceed to check for overturning. Check for overturning. So number 2, and before I can proceed to overturning, there is also another case for checking. There is also another case you can use to check for tension, which is, you can say or. Our first case is D is less or equal to 2/3, and our second case is E is less or equal to B/6. So our E is equal to D minus B/2, which is equal to our D is 4.267 minus 8/2. So 8 is the B, so which is equal to 0.267. So this is our E. So let's proceed and see. So from this you can say that 0.267 is less or equal to B. B is 8/6. So which is 0.267 is less or equal to, the answer to this is 1.33. So okay in tension. So you can either use this first case or use this second case. So we proceed to Roman 2, which is overturning. Check for overturning. And we know that for overturning, W times NB should be greater than W times X, or NB should be greater than X. So this is W times NB. This is NB should be greater than W times X, which is this distance from here to here. So in other words, if NB is greater than X, then it means no overturning. So let me erase here to create space for more calculation. So let's find this distance NB. So we have NB as from here to here. So to find NB, take 8 from here to here minus AN from here to here. So NB is equal to 8 minus AN. So this is equal to 8 minus 3.11. So which is equal to 4.89. 4.89. So let's see if there will be overturning or not. So this is NB, which is 4.89, is greater than X, is this distance from here to here, which is 1.157 meters. As you can see, it is greater than 1.157. Therefore, no overturning. Therefore, no overturning. Like that. After checking for overturning, we now proceed to checking for sliding. So Roman 3, check for sliding. Like that. We know that for sliding, F max must be greater than F. Like that. Whereby F max is equal to mu times W times W, capital W, which is this weight of the dam. So, and our mu is the coefficient from the equation, is the coefficient of friction between the dam and the soil, which is 0.55. So 0.55 times W. W is 1, is 14, 12, 64, 0. So you will get 77, 69, 52 Newton. So this one is greater than our F was 490, 500 Newton. Therefore, safe. Against sliding. We proceed to number 4, which is check for excessive compressive stress. So Roman number 4, check for excessive compressive stress. Which will be the last item. We know that Q max, or the maximum compressive stress, is given by W over B plus 6W times eccentricity over B square So our W is the weight of the dam, which is 1, 4, 1264, 0 over B is this distance from here to here, which is 8 into bracket 1 plus 6 times E. We have seen our eccentricity was 0. We calculated this earlier, 0.267 over B, this is 8, like that. So our final answer will be 211,940 Newton per meter square. So this is our maximum compressive stress. So as you can see, Q max is less than the permissible. We have been given the allowable compressive stress, so it's less than the allowable compressive, which is 34,330 Newton per meter square. Therefore, the dam is safe against excessive compressive stress. So therefore, the dam is safe against excessive compressive stress. And the question ends there. So in my coming session, I want to tackle something from either NEC or CDAC. So stay tuned as I will be proceeding to my next video. And remember to subscribe and hit that notification bell, and also to comment, like, and share to your friends. We meet again in my next session.